Okay, in this little mini lecture video, we're going to be starting chapter 6, and we're going to spend some time here because enzymes, what they are and how they work, is a big concept and a big chapter, so there's a lot to understand about them. The theory of biological catalysts, though, have been around since like the late 1700s. In fact, in 1926, that's when James Sumner isolated and crystallized the enzyme urease. So all the way back in the 20s. And he's the one that showed that enzymes were in fact proteins. So remember, we've looked at proteins already whose function it is to bind a ligand. So hemoglobin or myoglobin bind oxygen, antibodies bind antigens. So we have ligand binding proteins, and then we have enzymes that are proteins whose job it is to catalyze a chemical reaction in the body. They're classified and named based on the reaction that they catalyze. So oftentimes it will be some name and end in ASE. So that's how you can recognize that you have or you're talking about an enzyme. So for an example, a ligase is an enzyme that ligates or hooks things together. An isomerase is an enzyme that causes one molecule to undergo isomerization into another. So a lot of times you can figure out the function of an enzyme just from its name. So how do these enzymes work? How do they catalyze a biological reaction? Well, lots of ways. They use some organic chemistry, they use physical chemistry, they use inorganic chemistry. So we're going to talk a little about all of these different aspects and how they contribute to the ability of an enzyme to speed up a chemical reaction. So when you think about a chemical reaction, oftentimes we're talking about some reactant plus another reactant coming together to form a product or multiple products. And when we're talking about this reaction, there are two things that we have to consider in terms of its control. So one aspect is thermodynamic control. So thermodynamic control tells us the position of equilibrium. So the position of equilibrium. So that means when equilibrium has been achieved and the forward and reverse reaction rates are equal, is there more reactant or product around? If there's more product, we say it's a spontaneous reaction. If there's more reactant, we say it's non-spontaneous. So thermodynamics tells us strictly the position of equilibrium, whether or not we have more reactants or products. Kinetic control, on the other hand, tells us how fast it takes or how fast equilibrium is reached. Right? So one of the best examples I think we've already talked about is the combustion of sugar. We know that the combustion of sugar, the reaction with oxygen, has a highly negative delta G. So thermodynamically, its equilibrium position has more products than reactants. It's highly favored. It's spontaneous. However, kinetically speaking, the reaction is so slow that it takes forever to reach equilibrium. So that's why we don't ever get over that activation barrier, and we don't have to worry about our CNH combusting on the kitchen cabinet. So when we're talking about enzymes specifically, the reactants are now referred to as substrates. So a substrate or substrates are the molecule or molecules that the enzyme works on to do the chemistry. The chemistry takes place in the active site of the enzyme. So the active site is where the chemistry is happening on the enzyme. So it's the place where the reaction takes place. Okay, in general, we can write a schematic to show this. So we have an enzyme, represented by E, reacting with some substrate. They come together to form an enzyme substrate complex, represented by that little dot in between them. The chemistry happens, whatever that chemistry is, such that the substrate, which is the reactant in this reaction, is converted to product. So maybe I should write, we're talking about the conversion of S to P, so substrate to product. And then after that chemistry happens, the product is released from the enzyme, and the enzyme itself is regenerated, hence making it a catalyst in this particular chemical reaction. So we can use reaction coordinate diagram to really understand the difference between the thermodynamic versus the kinetic control in the conversion of substrate to product. So if I draw a reaction progress, so here's my reaction progress on the x-axis, the free energy on the y-axis, I'm going to show a thermodynamically favored reaction, so one in which the substrate is higher in energy than the product. So we know that if you're lowering the energy overall, you have a thermodynamically favored process. Okay, so when we're talking about the thermodynamic control, we're talking about delta G. Okay, so this is the thermo control. And the way I have it drawn, I have delta G less than 0. There's more products than reactants at equilibrium. This is a spontaneous reaction. So this is the thermodynamic control. Up here, represented by this double dagger, this is the transition state. So this is the point in the chemical reaction, sort of right before the bonds and the reactants get broken. I can't get it to right state. There. Ah, that's horrible. So right before the bonds are broken, this is the point right here where the reaction could go back to substrates or it could go all the way to products. So the reaction can go either way at the transition state. So when we're looking at the difference in energy between the substrate and the transition state, now we're talking about the kinetic control. And this is referred to as delta G double dagger. So this is the kinetic aspect of the reaction, how high this particular hump is. Okay, it's the energy required for the reaction to occur, right? So how much energy those molecules have to have, those substrates, when they collide for that reaction to proceed, for those bonds to break and new bonds to form as the products. In general chemistry, we refer to delta G double dagger as the activation energy, E sub A, but you have to admit saying delta G double dagger is a lot more fun, so that's what we're going to call it in this class. So remember, like with combustion of sugar, although a reaction may be thermodynamically favorable, this activation barrier may be so high that it doesn't occur at any appreciable rate. And that's actually true for a lot of biological reactions. They have a really high energy of activation, and in fact, on their own, they would never occur at a rate that would be amenable to sustaining life. So that's why we have enzymes. So enzymes function to lower this activation barrier. So if I drew another picture here with free energy, another reaction coordinate diagram, and reaction progress on the x-axis, I'll show another thermodynamically favorable one. So it might be that in this case, this might be the activation energy, delta G double dagger, of an uncatalyzed reaction, whereas in the presence of an enzyme, so here we go. Now for our enzyme catalyzed reaction, we have a new delta G double dagger. And you can see it's lower, so it's basically the enzyme has lowered the activation barrier for this reaction to proceed. So as we talk about the mechanisms in catalysis, we'll be doing some comparisons. So we'll talk a lot about how fast, oops, that's not right in yellow. We'll talk about how fast is an enzyme able to convert substrate to product? And we'll talk about how efficient is it in its job, right? So how efficient it is has to do with how well it can bind its substrate and how fast it can do its chemistry once the substrate is bound. So as we do this, we're going to come across lots of Ks. So it's important to remember, if we're talking about big K, we're talking about equilibrium constants. which means we're talking about delta G, which means we're talking about thermodynamics. If we're talking instead about little k's, then we're talking about rate constants. Those are related to delta G double dagger, the activation energy, which means we're talking about the kinetics of the reaction. So it's really important to keep those two things separate.